All right, we had some fun solving separable differential equations and what's the other one called? The integrating factor, using the integrating factor. Those are two methods we tried so far. Next, we'll move on to what we will call what is known as exact equations. Exact equations are equations of this form. It's going to be of m of xy. So m is some function of xy plus n of xy, also a function of x and y, times dy dx, or we could just write that as y prime, is equal to 0. So if the function is in this form and it's true that the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x, if this is true, then we call this exact. I don't know how to spell exact, but you know what I'm saying. This is exact. Why it's called exact, no clue. Didn't bother Googling it. Maybe I'll Google it and explain it to everybody in the next video. I don't know how to delete this. So yeah, here we have our exact equations. Let me go ahead and write this out again. So this equation I just had up here, 2x plus y squared plus 2x y prime equal to 0. This is in that mx of y. So this is m of xy, and this is n of xy. Now we can check if they're exact by using the formula I mentioned earlier. So this is m, this is n. Let's take the partial derivative of m with respect to y. What are we going to get? Well, x is just a constant in this situation. So the 2x term just goes away. And we're just going to differentiate y squared, basically. And that's pretty simple. That's just 2y. Now we're going to take this n term. We're going to take the partial derivative of n with respect to x. What is that? Well, y is just going to be treated as a constant, since we're taking it with respect to x. So this is really just the function 2xy that we're differentiating. And the derivative with respect to x of that is just 2y. So is 2y equal to 2y? Think about that long and hard. Ding dong, ding dong. Yes, it is. So that means this is an exact equation. So once we know that's an exact equation, what we can do is we can actually use this method of exact equations to solve this differential equation. You can find an equation of y in terms of x. What we want to do is find something called the potential function. The potential function is what we call potential because it's potentially a solution. So we'll find a potential function called f of x, y, and it'll be true that the partial derivative of f with respect to x is going to equal to m, and the partial derivative with respect to y is equal to n. That's just how the story goes. Okay, so how do we find this potential function? Well, we can either integrate m with respect to x or n with respect to y. Just both of these solutions are valid. You can take both approaches. For this demonstration, we're just going to integrate, not differentiate. We're going to integrate m with respect to x. So what are we going to get? And you'll see more of what I mean by potential function and how it works. So here, we're going to integrate this m term here, with respect to x. So we're going to integrate 2x plus y squared dx. What does that equal? That's going to equal 2x. The integral of 2x is just x squared. The integral of y squared is just xy squared, since y is treated as a constant. But we're integrating with respect to x. So out of this, we're going to get some function g of y. We're going to say that the function is called g of y. So we're not necessarily going to get a constant. It could be just a plain old constant, but it's going to be constant with respect to x. And just like with partial derivatives, and integrals, so once we integrate this function with respect to x, we're always going to get a constant. But what we know is that this equation is in terms of x and y. So that potential constant function is going to be a function of y. It will not be dependent on x in any way, but it could be a function of y. So now that we have this potential function here, we have this potential function. It's called potential function because it's potentially, a full solution. We can differentiate this with respect to y, and we'll see, if we differentiate with respect to y, it should match n. Because like I mentioned earlier, the derivative of f with respect to y will equal to n, and the derivative of f with respect to x equal to m. That's kind of how we work this out and figure out the actual solution. So we have this potential function. Let's just go ahead and differentiate with respect to y. So we're going to get f of y, we'll just say fy for short, is equal to, what are we differentiating with respect to? We're differentiating with respect to y. So we're going to get the x squared term is going to be constant, so it's just going to go away. The xy squared term is just going to equal to, so the 2 is going to come down. It's going to be 2xy. And then we're going to get plus. So what are we going to do with the g of y term? Well, we just know it's a function of y. It's just g of y. We don't really know what it is right now. So we can just say g prime of y. And, we're getting close to finding the full solution here. Now, as I mentioned, f of y is going to equal to n. And n is up here. So what we got is this. We got 2xy plus g prime of y is equal to 2xy. So what can we deduce from here? Well, so 2xy is on both sides. So we're really just going to get g prime of y is equal to 0. That's what we want to calculate. That's what we want to find here by setting these equal to each other. We really want to solve for the g of y term. So we have g prime of y is equal to 0. If we do the integration, we'll get g of y. One sec. G of y is equal to some constant c, because the integral of 0 is just a constant. So g of y is just some constant c. So it won't always be a constant. It's always going to be some function of y, g of y. But in this case, it turned out to be just a constant c. And so now we're done, basically. So we can now plug this constant in for g of y in our above potential function. So the solution is f of x, y is equal to x squared plus xy squared plus g of y. Oh, sorry, not g of y. Well, it is g of y, but in this case, we know g of y, so we're going to put c plus c. And some people prefer writing the term c is equal to x squared plus xy squared, because these represent like curves, and we'll get more into that in a future video. We'll explain how these represent individual curves. But this is the solution to the exact differential equation. And once again, you can plug this in to the equation up here and verify that it works. It's kind of a lengthy process, a little bit more lengthy than the integrating factor approach and the separable equation approach, but it's not so bad.